Please title these notes Applications 2 Notes, More Position Velocity Acceleration, and write today's date. By the end of this lesson, you should be able to solve position velocity and acceleration problems that do not require sign charts. So the first thing, there's a list of items that you just need to have memorized. As usual, if you don't memorize them, the dragon will come to your house and eat you. So make sure you do that. The first one is actually, the first two are ones that you already know. If f of x is the antiderivative of f prime of x, then that means that if we take the integral from a to b of f prime of x, then we're going to get f of b minus f of a. What's really key about that is it means that if we take the integral of velocity, we're going to get change in position. If we take the integral of acceleration, we're going to get change in velocity. Those are really key. We also know this one already. The average value of f of x from a to b is the integral of f of x from a to b, and then times 1 over b minus a. A couple of new ones. In these problems, you're going to be asked sometimes for the net distance traveled from A to B. So that just means that if Moving Man, for example, or let's say the Little Dragon, if the Little Dragon starts right here and then goes over there and then comes back over here and then goes over there again, then the net distance traveled is from where it started, way back over here, right to where it ended. However, the total distance traveled counts both the time spent traveling backwards and forwards. So goes forward for a bit, then goes backward, that still counts as distance traveled, forward, backward. If he just kept going forward and backward and forward and backward and forward and backward for a long time, he could go for several miles and still have only in a total distance traveled, while the net distance traveled might still only be from here to here. So the net distance traveled is just the integral from A to B of velocity. It's basically saying what was the ending position minus the starting position. Whereas the total distance traveled is the integral of the absolute value of the velocity, saying that we don't care which direction the dragon was headed, it's just how far did it travel overall. These last two you already know. The integral can also be expressed as the area under the curve, and the derivative can also be expressed as the slope of the tangent line. Those are going to come back into play again. One of the things to be aware of when you're asked for these things, or if you're just asked for the value of position, velocity, or acceleration at a specific time, you do not need to use the sign charts like we did before. Those were being used for maximum, positive, negative, increasing, decreasing, those sorts of problems. So let's look at some examples of what we'll see for this type. So these are examples. If position is given by x of t equals 6x to the fourth minus 2t cubed plus 1, what is the acceleration when t equals 1. So in this case, we're not asked about when it's increasing, decreasing, minimum, maximum, whatever. All we're asked for is the value. So all we need is to find an equation and then plug 1 in for t. So we know that x of t, position, is 6x to the fourth minus, oops, this should be a t, my bad, plus 1. The derivative of that is velocity, so that would be 24t cubed minus 6 t squared, and then the derivative again gives us acceleration, 3 times 24, 72t squared minus 12t. So to find a of 1, when t equals 1, I'm just going to plug that in. 72 times 1 squared minus 12 times 1. A of 1 equals 66. For these, we like to have units on them. Again, I didn't put units in this problem, but we'll say that position is in meters, time in seconds. So that means the 66 meters per second squared. Let's look at a few more. The velocity of a particle is given by v of t equals 3t squared minus 4. So our first problem, let's find the acceleration at time t equals 3. Again, we just want an equation for acceleration, so we're starting off with velocity. We can just take the derivative and then say, okay, when t equals 3, 6 times 3 is 18. One thing, it's not so much of an issue for this problem, but for more advanced problems, when we have the calculator, we can do the following. We can do n-deriv. So let's see, that's math 8. And then we can put in our 3t squared variable, and then the number that we want it at, and lo and behold, that gives us the same answer, that 18. You will occasionally run across problems where you can use a calculator, but you really can't do the derivative by hand very easily. Make sure that you know about that shortcut. Going the other way, we could also say if the position at time t equals 0 is 5 meters, what is the position at time t equals 3? Since position is the antiderivative of velocity, that means if we take the integral from 0 to 3 of v of t dt, that's going to give us the position at time equals 3 minus the position at time equals 0. Now we know that the position at time equals 0 is 5 meters, so I can pop that right in here. We're looking for this. And we can find this. This is the integral from 0 to 3 of 3t squared minus 4 with respect to t. When we simplify this, that's 15 minus 0 equals position at time equals 3 minus 5, so we add 5 to both sides. Got 20 meters. this same idea works if we know something about acceleration and want to find out something about velocity. So for example, if the acceleration is given by a of t equals 4t minus 1, and the velocity at time 0 equals 1 meter per second. When is the particle at rest? Remember, particle at rest means v of t, whatever t is, equals 0. We're looking for when, so that means we're solving for t. Specifically that t right there. When does v of t equal 0? So because velocity is the antiderivative of acceleration, that means the integral from a to b of a of t dt is velocity at one time, that top time, minus velocity at that other time. Now, the thing is that we don't really know exactly what these two velocities are. We know that when time is 0, v is 1, so clearly one of our bounds is going to be 0. We have an equation for a of t, 4t minus 1 dt. We can see that this right here, this a is 0, so we've got minus v of 0. But we don't know what this time is. That's what we're trying to find. So let's just let that be x. We're going to solve for x. And then this is some time v of x. Don't know what that time is. But we can still do our integral and everything, and we can still do some substitutions over here. We do know what v of 0 is. It just told us it's 1. And we do know that we're solving for when the particle is at rest. That means that at this second time, we know that the velocity is 0. So now we're just going to solve for x over here. 4t squared divided by 2 minus t from 0 to x. So that's 4 divided by 2 is 2x squared minus x minus 2 times 0 squared minus 0 equals 0 minus 1. So 2x squared minus x equals negative 1. Add 1 to both sides. Now we can just solve that by factoring. Oops, I made a mistake up here in the problem. This should have been minus 3. I changed it as I was doing the problem, and I didn't change it later. Should be negative 1. That's positive 1. There we go. So when I factor that, 2x minus 1, x minus 1 equals 0. So x equals 1. X equals 1 half. So what that means is it means the particle is at rest at 1 second and at 0.5 seconds, or a half second. Either way is fine. There are also a lot of good problems we can get from graphs. So let's look at problem number 4. We're going to do a bunch of parts on this. So the velocity of a particle is given by the graph. And here's this right here. And our first problem is, what is the acceleration of the particle at time t equals 3? So the key things to remember here are that acceleration is the derivative So acceleration is the derivative of the velocity, and the derivative is the slope of the curve at that exact point. So when we go up here to where time t equals 3 right here, what we want to do is we want to say, what's the slope of this line? Well, this curve is flat, the rise is 0, so it's a slope of 0 right here. So our acceleration is simply 0. If we had said, what is this acceleration at time t equals 1, we would have said, what's the slope right here? And then we would have done rise 1, 2, 3 over run 2. But because the curve is flat at t equals 3, so the slope, acceleration, is 0. There are a bunch more questions we can ask with this. I'm going to bring the little graph along for the ride. What is the position at time t equals 4 if the position at time t equals 0 is -1? Well, we know from before that position is the antiderivative of velocity. So that means that the integral from, let's see, 0 to 4 of the velocity is position at time t equals 4 minus position at time 0. Now we know when t is 0, position is -1. Position at time t equals 4 is what we're trying to solve for. And the key thing to remember here is that the integral of the velocity from 0 to 4, this is the same as the area under the curve. From 0 to 4. So if I come over right here, I'm looking for this area from here to here. So this, let's see, that's 3 times 2 divided by 2, that's 3. This is 6. If I add that up, the area under the curve is 9. Subtract 1 from both sides, and there we go. Now, these are some of the newer ones. Let's say, what is the net distance traveled from t equals 4 to t equals 7. And this one you have to look back on that original piece of paper that I had you memorize. Net distance from A to B, right here, that's just the integral from A to B. It's basically the change in position. The net distance traveled is how far we were at the end minus how far we were at the beginning. So net distance from 4 to 7, integral v of t dt. Again, area under curve. Remember, this is the signed area, so we're going from 4. So this is 1 times 3 divided by 2, so this is 1.5. This is going in the negative direction. It's negative 3 times 1 divided by 2, so negative 1.5. And then 7, that area is negative 3. So when we're doing this, we've got 1.5 minus 1.5 minus 3, or a net distance traveled of negative 3 meters. Let's see, it should be meters. And what that means is it means that at time t equals 7, the particle is 3 meters to the left of where it originally was. This, however, is different from the total distance. Remember again from that first page that I had you memorize, total distance. That means that here, when we're traveling 1.5 meters to the right, that's part of the distance. But then this 1.5 meters here and this 3 meters here where we're traveling to the left still counts as distance in terms of total distance. So the total distance from 4 to 7 is the absolute value of v of t dt. And so what that means is it means instead of subtracting these negative areas, there is no negative area basically. We're just going to add what's down here. So where before we had 1.5 minus 1.5, here take the absolute value. So that means that even though at the end we ended up 3 meters to the left of where we started, we traveled 6 meters overall, some forward and then some back. Another thing we can be asked to do is to write equations based on our little graph. Generally these will just be simple linear equations. Actually, I guess they're expressions. Write expressions for the particles, acceleration, that's a of t, velocity, v of t, and distance, x of t, from the origin that are valid for the time interval when t is between 0 and that should be a 2. Now this funky wording here, valid for the time interval 0 to 2, all that means is it means that we're only looking right here when t is between 0 and 2. We don't care about anything else, which is good because this is a different equation for this line than that line, than that line, than that line. So let's just start off at the top. Notice, by the way, that distance is going to be x of t, not p of t. Make sure that you write that correctly at the end. Let's see what we've got. So first things first, we have a graph of velocity. what is the equation of the line from 0 to 2? Let's go ahead and write this in y equals mx plus b form, or v of t equals mx plus b. First thing that we want to know is our slope. Second thing we want to know is y-coordinate of the x-intercept. So I can see right here that the slope 1, 2, 3 over 2, and I can see that the y-intercept is 0. I could also have done this by observing that there was a point right here, and doing it with the formula that looks like this. Y minus 0 equals 3 halves, x minus 0, end up giving you the same thing. Just make sure you substitute the vt, which is what we're looking for, in for that y. So once we have an equation for velocity, or an expression, I should say, for velocity, then we know that the acceleration is the derivative of v of t. So we can just do that derivative. If v of t equals 3 halves x, then a of t is just 3 halves. Going the other way, x of t, which remember is position, is the antiderivative of v of t. Oh, there's one piece of information that I forgot to write in the problem. When t equals 0, the position is -1. So x of t is the antiderivative, so let's take the antiderivative of v of t. Whoops, I just need to go back up here. So notice up here that I have an x here, but I have a t here. That means, because this is supposed to be in terms of t, that means I should have a t right there. Likewise here, x is my variable for position. My input variable here is t. That should be 3 halves t dt. So when I take the antiderivative, I'm going to add 1 to the exponent, divide by the new exponent, this is plus c. Three halves divided by 2 is 3/4. But the thing is, we don't want to just leave this plus c here, so we substitute in when t equals 0, x of 0 is -1. So that means that -1 equals 3/4, 0 squared, plus c. c equals -1. So our final equation is right like that. Two more problems and then we're done. So let's say that we're told that v of t is t squared minus 4. And our first question is to find the total distance traveled from t equals 0 to t equals 5. So we know that total distance is going to be the integral from 0 to 5 of the absolute value of v of t, so that's 0 to 5, absolute value of t squared minus 4 dt. What I'm going to use for this is I can just use that finite integral. The command you're going to use is the ABS command. So t squared minus 4, comma t, comma 0, comma 5. And when you put that in, remember, your absolute value on these calculators is going to be right there, math and then number. And on the TI-82s, it's right over here above the x to the negative 1. You just do second, and then it's right there. When we do that, that's going to give us a number, 32.333 meters. Another question, what is the average velocity on the interval 0 to 5? Remember, average value for anything is going to be 1 divided by, subtract the two parts of the interval, this is something you just have to memorize. Memorize this formula. It's going to come in handy a lot. And then when we plug that in the calculator, we get about 4.3 repeating. Okay, now on to our final problem, something slightly different. The following table gives values for the velocity of a particle moving along a straight line could the graph at right be a graph of the position of the particle? So here's the chart. And here's the potential position graph. And it starts out like this. That kind of curves up over there, flattens out, curves back up again. So, one of the key things to remember, velocity is the slope of the position graph. So what this means is that means at time t equals 0, the slope needs to be positive 1. Could be. Right here, that's definitely a positive slope. But here it says that the slope, the velocity, is negative 2. That's definitely not true. Could not be negative 2. It could be 0.5, it could be, some other positive number, but it's definitely not negative. So we can stop right there and we can say, nope. Velocity is the slope of the position curve at time t equals 1. The slope of the curve is positive, but the velocity is negative. Okay, that concludes the notes for position, velocity, acceleration 2.